One of the most prominent topologies of power supplies used in everyday life applications such as mobile phone chargers, laptop chargers, and similar applications is a flyback converter. Technically, a flyback converter reminds us a lot of a buck boost converter, with the difference that the inductor now is replaced by a transformer. The transformer has N1 primary turns and N2 secondary turns. Note that we have the dots indicating the start of the windings, which can be freely chosen for one of them, and then the other one is fixed. And they have to be connected like that. If the dot would be up here on the secondary side, it would not work. As we did with the non-isolated converters, we can investigate the operation of a flyback converter in the first stage from 0 up to the duty cycle when the switch down here is closed. That means we have the primary winding directly connected to the voltage source, so we have the input voltage across the primary winding. The current is flowing into the dot of the transformer, and it cannot flow automatically out of the dot on the secondary side as this diode here is blocking. That means the magnetic core inside the transformer is getting magnetized. It stores the energy in its H field, and the electrical field from the capacitor, the charges stored in the capacitor, provide energy to the load out here. Through Faraday's law, we have a voltage coupling from dot to not dot from the start of the winding to the end of the winding, transferred from the primary side where we have V in across N1 to the secondary side N2 divided by N1 times the input voltage. During the off time of the switch from duty cycle until the period time t, the switch here is open. That means there cannot be any current flowing on the primary side of the transformer. We used to have current going into the dot here from the first stage. That means the magnetic flux still needs to keep its direction. It cannot jump. So the current is now going still in the secondary side into the dot end of the winding, forcing the diode to be forward biased, charging the capacitor, and supplying the load. The conducting diode again can be modeled as a short circuit. That means that the capacitor voltage, the output voltage across the capacitor, is also applied to the secondary winding, now from the non-dotted end of the winding, so the end of the winding, until the start of the winding in a positive way, V out over here. Again, through Faraday's law, that output voltage couples back to the primary side. Now the cause is on the secondary side and the result is on the primary side, meaning we have from the non-dotted end to the dotted end the transferred output voltage and transferred now down with the ratio N1 divided by N2. Looking at Kirchhoff's voltage law on the primary side, we have that voltage that is transferred back from the secondary side in series with the input voltage, and both of them are adding up to the total voltage across the switch. That means the potential up here on the drain of the MOSFET here is higher than the original input voltage provided by the source. That also means that we need to use a power switch that is rated for higher than the input voltage, where the overhead voltage on top of the input voltage is the one coming transferred back from the secondary side when the switch is off. The DC transfer function of a flyback converter in continuous conduction mode is basically the same as the one we had for the buck boost, but now just multiplied with the transfer ratio of the transformer. Again, we have similar limitations when we are approaching to the duty cycle of 1 From the forward voltage drop of the diode, all the resistances in the components of their parasitics, and the fact that the time is getting too short to actually charge the capacitor and provide energy to the load. Therefore, our assumption in the averaging approach to derive the equation up here that the voltage across the capacitor is constant no longer holds, and we cannot realistically operate a flyback converter close to a duty cycle of 100%. But in this case, any voltage amplification or reduction can be achieved by choosing the correct transfer ratio of the transformer. In lots of practical applications, the flyback converters are used to transform the rectified AC mains voltage down to a level that is used by the application. As I previously said, for example, mobile phone chargers, the rectified 230 volts or the rectified 110 volts get transferred down to something in the 5-volt range. Realistically, many flyback converters can be built with an efficiency beyond 90%, and practically they are often used in applications up to a few hundreds of watts.